So hello everyone, today I will talk about the Laplace equations and how to solve it for the groundwater model. So in here I have a Laplace equations for the situations of the steady state flow homogeneous with isotropic for the confined aquifers. For the equations, I will try to solve it for the numerical methods, and particularly finite difference methods. So from these equations, I try to revise in here, and in here I just try to solve it for the two dimensions, x and y directions. So with the first term for s, I have in here, you just apply the finite difference methods. Okay. So this one is the name of the finite difference methods. You can search more for information about this, and you can understand why I have the equations in here for the s and y directions. So apply the finite difference method. I have the term for s, the partial. This one is the partial derivative equations, and for the partial derivative of s, I have the equation like this, and for the y I have the equation like this. So in here you see we have the I and j nodes. So in i's in here, i's represent the positions of s directions, and j represent the positions of y directions in here. So that's reason why it's have the difference between the two equations like this. So and when you derive the equations, follow the s and y direction, and just plot this like this. S, you have the s plus the term of s plus the term of y like this equal 0, like this kind of original equation we have before. So in here I just consider the delta x equal the delta y. Delta x and delta y is the distance between the nodes for your grid. And in here, actually in here is will be have the tx and ty in here, but in these situations I also consider the ts also equal ty. Yeah, so this is our this is our conditions for the equations, and from this you can have the final equations for your Laplace equation using the finite difference methods like this kind of formats. So the next step, we will try to build a system equations for your grid. And in here I have an example of the grid with the 1 2 3 4 1 2 3 4 4 4 4. Yeah, we have 16 nodes. So what does this mean? You can see here I have the final equations of the Laplace equations in here, and in your grid this one is a small example for the grid with the 16 nodes. It means you will have 16 equations for your matrix. Okay, and here it indicates for the system equations we will build right now. Okay, for the groundwater flow, we usually consider the bottom and the top boundary. It will be the no flow boundary like this, and the left and the right we will have specific values. For example, in here I have the 50 on the left and 5 meter. For example, 5 meter on the left and 50 meter on the left and 5 meter on the right. For example, the variable we consider here will be the s. S is mean the hydraulics head. Okay, and the top and the bottom boundary will be have the no flow in here. So for no flow boundary, we will have the equations, the potential of S, potential derivative of S over potential of Y equal 0. So we have to solve it and combine it with the Laplace equations we derived before to make a system equations. Okay, and so in this one is the final form from the Laplace equations we have already derived before, and this one is the equations for your no flow boundary. So we got the Laplace equations already. So right now I try to derive the equations in the no flow boundary. So in here we have the potential of S over potential of Y equal 0. So it means that in here we have the Sij plus 1 minus Sij over delta Y equal 0. And from here we have the final equations like this: Sij plus 1 equal Sij. So what does this mean? So you just look at the i's positions in here. It means in these equations just consider the positions follow the y directions, and just from here you just look at your grid in here, and you can understand like that way. It means from this equation, it means your value is this node, the nodes on the node lies on your no flow boundary will be equal this node. This one equal this one. This one equal this one. This one equal this one. And for the top equations also the same. The S1 4 will be equal the value as S1 3, and S2 4 equal to S2 3, like this, because you derive the equations of no flow boundary like that way. So it's the meaning. Okay, the next step we will build a system equations for the grid. Okay, in here just make first equations for the node S11. So because we understand from this no flow equations, no flow boundary and derived equation, so we understand that the value as S11 will be equal the value as S12 value as S11 equals the value as S12. So that's the reason why we have the equations like this. And from here we have this equal 0. So the first node we have. So the next one is the S21 here equal S22. We have this here, S21 equal S22. So we have this. The same with this, with the S31 equal S32, S41 equal S42. So we have this and this. And how about S12 is equal what? So because just look at the positions of S12, you have the positions of S12 is lie on the boundary on the left. So it means that the value of S12 will be equal the value of the boundary on the left. It will be equal 50. So it means you will have the equations of the S12 will be equal 50. Okay, the next one is the positions of S22. So in here you see is the S22 is the internal nodes in this grid. So in here you have to apply the Laplace equations. This one, the Laplace equation you have already derived. So this one. So because S22 just consider is the center nodes. You consider S22 is the center node like this. As Ij will be the S22 in these situations. So it means in here you have the coefficients of S22 will be equal -4 like this. Yeah, you have -4 like this. And the nodes of I plus 1, I minus 1, S of J plus 1, and S of Ij minus 1 will be the positions distribution all around the S22. And all of this will have the coefficients equal 1, right? Because the in the before of this node is have the coefficients of 1 like this. So because of this, you will have the equations of S22 like that. So just look at this. You have the S22. You have the coefficients equal -4. So in here you have 22 coefficients -4. So all around this you have the S12 here. Coefficients 1. You have S23. Yeah, you have one S23 like this. The next point will be the S32. You have S32 in here. And the final ones is the S21. You have one S21 in here. So you finish the equations in this point. And the next point is the same. The next point for the S32 will be the same with the previous one like this. So you have S32, the coefficients of this will be -4 like this. you have the minus 4 in here. And the all round, the nodes all round of S3, 2 will have the coefficients of 1 like this. Here, 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 and here will be equal 1. I mean the coefficients, and equal 0. And how about the S42? S42 lies on the boundary on the right, and it will be equal 5. We already defined it in the beginning. And here you have S42 equal 5. So this one, this one, this one, this one, and another node will have the same way to build the equations. Yeah, so you can use this kind of equations, this kind of way to build another points for your grid. So that is the way to build the system equations. And then you have a system equation. You will have to transfer your system equations to a particular matrix like this. Okay. Just relies on your equation, your reveal system equations. You have the matrix form like this. And how to rearrange this? Okay, the first one just consider the first equations of S11 and S12. So in here you have the equations of S1 minus S12 equal 0. So you just put it in your matrix. Yeah, so in your matrix you have the S11 in here is the variable you have to find in the ends. So S11 coefficients, your coefficients will be 1. You just put the coefficients in here, it's 1. And as the S12, you have the coefficients of minus 1. Minus 1 here, you should put the minus 1 here. And how about another point? You don't have the value of another point, so you just put the 0 value in there. And the B column, you have the 0 in here, and you just put the 0 in here. Okay, the next one for the equations of S21 and S22. So the same with this kind of the same with the reverse one. You have the S21 you have the coefficients of 1, put it in here, 1. Coefficients of S22, you have the minus 1, you put the minus 1 here. And another ones will be 0. The B column, you have the 0 in here, you put the 0 in here. And this one is the same, right? Okay, go to the center point. Okay, in here you have a point lie on the left boundary, and is equal the value of the here. You have a 1 point, the S12 lies on the boundary, the left boundary of your model, of your grid. So you just have the coefficients of 1 in the X, 1, 2. Here, 1 SS 1, 2. We have coefficients 1 here, 1, 2. And the B column, you have 50. because the value of S1, 2 equal the value at the boundary is lie on, right? Okay, and S2, 2 in here. S2 is the interiors, no. The center, no. Put it in the matrix form. You have the minus 4 for the S2 in here. You have the minus 4. And the routing point of S2 you have the coefficients of 1. So you just put the 1, 1, 1, 1 in here. For the nodes of S2, 3, S3, 2, S1, 2, and S2, 1, like this. Like these equations. Okay, and the column of B will be 0. Yeah, 0's in here. Yeah, the same with the coefficients, the same with these equations of the center point of S3 to like this. You have the minus 4 for the S this, and you have the minus 4 for the X3 2 in here, and the coefficients of 1 for the points all around of the center points of S3 2 like in here, and the column B you have the 0 in here. And for the X4 2 equal 5 lie on the right boundary, and you have the coefficients of S4 2 have the coefficients of 1, and the column B you have the 5 here, and another point will be 0 like this. So that's the way you have a matrix for the Laplace equations. And this matrix will have the form like A x equal B vector. So just try to solve this kind of matrix. You will have the S value, the value you want to find for your model. Yeah, and that's this one is the way to solve the Laplace equations for the groundwater model. Thank you for watching.